In the last lecture, we derived the least squares formula, which says that if you have independent data measurements x and dependent data y, and you're looking for the coefficients stored in some vector m that give you a polynomial of best fit, then m equals A transpose A inverse A transpose y, where A is a matrix that you create based on the type of polynomial that you're looking for and the data measurements x. We concluded with this example, where we had these 4 data points. So each of these is some measurement x, y, and we found the best fitting parabola. We're going to pick up with this example in this lecture. So now that we have this degree 2 quadratic polynomial for this data, let's do a calculation that shows how closely this model fits these data points. Our notion of closeness is something that we measure with the residual vector and the r-squared calculation. The vector r that we identified as the altitude that we would drop down if we wanted to go from our original measured data y to this plane of all the ways to do a times a vector of coefficients. This vector r is our residual vector. And what our least squares computation has done is minimize the length of that vector. Now that we have y, and given our algorithm we have m, we can compute the residual vector in terms of y and m as y minus a times m. Or if you wanted to avoid the new notation m and give a formula which is expressed entirely in terms of y and a, the objects we started with, what you could say is r is going to be y minus a transpose a, all that inverse, times a transpose y. Oh wait, that's not quite correct because a transpose a inverse a transpose y is just the coordinates of m. I need to act on m with a. So let me slide this over. And we need to do a out in front. So the rest of this expression that a is acting on is the vector of coefficients m hat. So that's a formula for the residuals entirely in terms of a and y, and you could compute that directly without computing m. Let me show you what that looks like in MATLAB. All right, here's where we left off with MATLAB. So we had set up the matrix A and the vector y, and then we did the inverse of A transpose times A, and then that times A transpose times y. These are the coefficients m that we're looking for, so let me just store them in a vector called m. So now if I run m in the command window, it returns those numbers. We can plot the data and the function now, so let me set up an anonymous function of x, which is going to be the constant first, plus m2 times x, plus m3 times x squared. So that's how you have to order the coefficients in m. Then we can do hold on, scatter the x data, so 1, 2, 3, 4, or you could extract the second column of A. The y data, let's make it filled. How about point size 10? Okay, so there's our data points, and then let's add to it the function plot, so f plot f, and let's go from 0 to 5. Whoops, I forgot a comma. There we go. Now I'm going to change my axes a little bit, so let's go from 0 to 6 on the x-axis, but 0 to 10 on the y-axis, like that. And then we will turn a grid on. Actually, let's go 0 to 5. Okay, so there's our plot of the data points together with the function. We can compute the residual vector r by doing r equals y minus a times m. If I display this down in the command window, it returns the values 0.2, negative 0.6, 0.6, negative 0.2. These four measurements tell us how far away our function is from the actual data points. So if you look at this first data point, that first coordinate in the residual vector r is telling us that our measured data is 0.2 higher than our function. The second point is 0.6 lower than the model. The third point is 0.6 higher than the model. And the fourth point is 0.2 lower. People like to look at the residuals to see how close the model is to the measured data points. Now, if your residuals were all 0, then your model is perfectly passing through the data points, but that doesn't necessarily mean that it's a good model. For example, you might have a large collection of data which is roughly linear, but a line doesn't pass through it. However, a degree 17 polynomial might perfectly pass through it and give you a residual vector of 0, but that doesn't mean that that degree 17 polynomial is a good choice. So while the residuals can give you an idea of how good of a fit the model is, that doesn't mean that you should aim to have residuals of 0. The r squared value of our model is going to be 1 minus the sum of the measured data points minus the model data points. In other words, it's the gap between our actual data and what the model predicted, divided by the original data points, each one minus the average of all of the data. Now this numerator, the gap between our actual data and what the model predicted, this could just be written as Ri. So for the parabola best fit that we were looking at, it's going to be 1 minus R1 squared plus R2 squared plus R3 squared plus R4 squared. And then we'll write out the numerator. Let me remark here that y bar, this is the average measured y value. So this will be the measured data y1 minus that y bar squared plus y2 minus y bar squared plus y3 minus y bar squared plus y4 minus y bar squared. Okay, this first form I've given you is how r squared is normally expressed in a textbook or something like that. I've expanded it over here on the right because it gives you an indication of how we could do this efficiently in MATLAB. So in particular, we have the sum of squares of entry in a vector. So we could take that first expression, or rather the expression in the numerator, and write that as the residual vector dot itself. And then for the denominator, it's the same idea. It's a bunch of coordinates squared. So we could think of this as, I don't have a nice way to write this, but how about y1 minus y bar, y2 minus y bar, y3 minus y bar, all the way through y4 minus y bar, that vector dot itself. And then there's an easy way to do dot product of vector in MATLAB. Here's how we'll compute the r squared values in MATLAB, so we can call it r2. And it's going to be 1 minus dot r with itself divided by dot y minus mean y, y minus mean y. So this is going to do what our denominator needs. If we run this, we get an r squared of 0.98. Your r squared is 1 when your residuals are 0. You would see that up here in this numerator, so it would be 1 minus 0. So an r squared value close to 1 means that the model is fitting through the data pretty well. Let's end today with a few more remarks about the least squares algorithm. We'll stick with this data set of 4 points that we have on the left. What would happen to A if instead of trying to fit a quadratic, I wanted to fit a cubic? So we'll set up A and then we'll do it in MATLAB so that we can see what the r squared value would be. Okay, so what we want is for each data point, yi to be equal to some constant m1 plus m2 times xi plus m3 times xi squared plus m4 times xi cubed. So now if I set up my matrix A, it's going to look similar, but it picks up a fourth column. So our first column is going to be 1, 1, 1, 1. The second column were the x coordinates of the data, which happen to be 1, 2, 3, 4. And then the third column, just like before, it's going to be those x coordinates squared. So 1, 2 squared, all right, 1 squared, 2 squared, 3 squared, 4 squared. And now we also have a cubic term. So we'll have 1 cubed, 2 cubed, 3 cubed, 4 cubed. In the past, our matrix A was tall. We have more rows than columns. Here it's square. If we're solving for the unknowns m1, m2, m3, m4, this means we have 4 equations for 4 unknowns, rather than, say, 4 equations for 3 unknowns or something like that. So instead of an overdetermined system, we now have a square system. So what does this do to our computation? Okay, we're back in MATLAB with all the same work as before, but I'm going to take A and just add another column onto it. So 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. Our least squares computation now is going to give us a fourth term, so let me add on to my anonymous function on line 8 plus the fourth entry in m times x cubed, and then I think everything else is going to be the same. Okay, I have both the parabola and the cubic on there. Maybe that's not a bad thing, but let me add up here, clear, close, CLC, just to wipe everything out. Okay, here's my 4 data points with a cubic. My r squared value is 1 because if you look at the residuals, they're all going to be 0. You have to be a little bit careful here because in MATLAB they don't look like 0, but actually they are. So MATLAB isn't quite landing on 0, but it should be 0. So this would be like 0.00000, you know what I mean. Okay. Here are the coefficients m. So -5, 4 2/3, etc. We could actually solve for n this time by just doing inverse of a times y. Gives us the same numbers. That wasn't an option before because you can't invert a tall matrix. So perhaps this is some collection of data that we've recorded, and we realize now that a degree 3 polynomial would give us an r squared value of 1. But that doesn't necessarily mean here that it's a better model for the situation than the quadratic polynomial. Because if I add in another data point, say I took 5 measurements, we're no longer going to have an r squared value of 1. Does that mean that our model should have been quartic, like we should go up to another one? No, not necessarily. So the big lesson here is just because you could fit a model perfectly to data doesn't necessarily mean that it's a good choice. What would A look like if I did try to fit a quartic polynomial but to my original 4 data points? Well, it's going to be the same matrix as before, so let me just copy that. But we're going to pick up a 5th column that would look like 1 to the 4th, 2 to the 4th, 3 to the 4th, and 4 to the 4th. This is now a wide matrix. It's an underdetermined system. That means that there are more variables than there are equations. Trying to fit a degree 4 polynomial through 4 points, it's like trying to fit a degree 1 polynomial through 1 point. So if you're just given 1 point, what's the line of best fit? Doesn't make any sense. Same thing for 2 points in a parabola. There is no uniquely determined function that would fit. I think it's really natural during this whole discussion to wonder why we're bothering to actually learn what's going on behind the scenes when something like MATLAB or Excel does a line of best fit, especially if we assume that we're going to use technology to actually compute the coefficients using the A transpose A inverse A transpose Y formula. One reason why I'm happy to know least squares is that you can actually design the resulting polynomial a little bit more than you can if you just ask MATLAB to do the best fitting degree 2 polynomial, for example. So I would say that using a program to generate a polynomial of best fit versus doing it yourself by setting up the matrix A and the vector Y, it's kind of like the difference between driving an automatic car that does all the shifting for you and driving a manual. Now, I say this as somebody who cannot drive a manual car. I tried to learn. I was really terrible at it. But technically, if you drive a manual car, then you have a little bit more control over what's happening. You get to decide what gear you're in, for example. So I hope our final two examples in this lecture demonstrate how you can exert a little bit more influence over the resulting polynomial than you might be able to if you just punch everything into a calculator. Okay, I picked this first example to drop in a little bit of history. So Raleigh, the capital of North Carolina, was intentionally founded in the year 1792. I guess that's when they got a charter or something like that, in the middle of North Carolina, in a place that did not have a previously inhabited town or city. So nobody was living there. They planned it to be the state capital, so it's one of the few capitals in the United States that has that distinction. The census takes place every 10 years, so you can check the population of Raleigh from 1800 to 2020 by looking up census data. So here I've put all of the census data measurements for the population of Raleigh from 1800 to 1900. So you can see for the most part the population grew. For some reason, I'm not sure why, it'd be interesting to know why, but there seems to be a drop off from 1820 to 1830, but then it goes back up a bit to 1840. We are going to do a line of best fit for this data. And what we're going to do is start with the year 1790. I picked 1790 because we have increments of 10 years here, and the beginning of Raleigh was 1792. So we'll pick 1790 as year 0 for our plot, and we will insist that because nobody was living there in 1790, our line must reflect that. So we'll say that 1790 had population 0 on our best fitting line. In other words, what we're going to do is plot the population over time, add the line of best fit, and we will insist that that line passes through the origin. Now, that's not something that you can necessarily do if you just say, give me the line of best fit, because it's going to give you the slope and the y-intercept, and it might be the case that the y-intercept is not 0. So here what we're going to set up and solve is find the line of best fit, which must have a y-intercept of 0. Such a line would have the form y equals m1 times x. Before we switch over to MATLAB, let's identify a few more pieces of information. The year, this is going to be like our x vector. This is independent measurements. The population is the dependent y vector. We have 11 data points. So if you look at the dimensions of our calculations, what we call n is going to be 11. And then notice that A has a column for every coefficient of the model that we're looking for. But here we only want one coefficient. So A is going to be 11 by 1. In other words, it's going to be a single column, and what will be in that column is the X data. Okay, let me switch over to MATLAB Online so that we can do this. Okay, so here's an M file we can start with. I'll save it as Raleigh population. What I've done here line by line is I've created a years vector just going off of the numbers that are easy to see. So I'll say let's make an increment vector that starts in the year 1800, goes up by 10 until it gets to the year 1900. But actually, I want the year 1790 to be 0. So instead of doing mental math, I'm just going to take this vector and subtract 1790 off of each entry. So if I do that, it goes from 10 is now 1800 through 110 is now 1900. And then I just took the transpose. So this is the new years vector. I took the transpose so that it has the same shape as the population vector, and then also A should be a column. Here are those population numbers. So this is in the year 1800. And this is the year 1900. Okay, now let's set up our least squares calculation. So our matrix A, normally I would have a more interesting matrix, but here it's actually just going to be the years vector. I don't even really have to define a new quantity called years. But just to use all the same terminologies in our previous work, let's call it A. And then M is going to be the inverse of A transpose times A, and then all of that times A transpose times the Y vector, which is the pop vector. As expected, M is just a single number. In other calculations, it's a vector of coefficients, but here it's just a single number that's giving us the slope. We know that the y-intercept is 0. Now I will set up my line as an anonymous function, so we'll have f equals an anonymous function of x, and it's just going to be m times x. Okay, now I can do, let's do hold on, so we can do the scatter plot and plot the function. We'll do scatter years pop, and let's make them filled. And then we'll do an f plot of f from the year 0 through the year 110, so that's 1790 to 1900. We'll do grid on, and then we'll label the x-axis time since, or how about years since 1790, and y label population. And then we'll just give it a title, population of Raleigh in the 19th century. Okay, so here's our plot. You can see our data points, the line of best fit, and the way we did our least squares calculation, the line of best fit must pass through the origin. So we didn't ask it for a general slope and y-intercept, we set it up so that the y-intercept for our best fitting line had to be 0. In other words, this isn't necessarily the line of best fit, rather it's the line of best fit which passes through the origin. So given that condition that we're imposing on the line, this is the best we can do. Now, it doesn't look to me like this data set is particularly linear. In fact, if you look at the growth of Raleigh over time, it doesn't follow a straight line at all. But I just wanted to give you this as an example. Let's finish our least squares discussion with this example. So if you're driving down the road and you have to hit the brakes in an emergency, how long does it take your car to stop? Turns out the total distance that the car is going to travel during this emergency braking situation depends on two different quantities. One is the distance it travels during your reaction time. So does it take you 1 second, 3 seconds? That can actually have a big effect on how far you go, especially at a high speed. And then there's also just the physical amount of time it takes for the brakes to stop the car. So let's look at this. I'm going to neutralize some of the other conditions, like how long does it take the driver to react? Different drivers are going to have different reaction times. Different people will have different reaction times depending on the time of day and their road and whether or not they're fiddling with the radio or something like that. So let's assume for this purpose of this exercise that all drivers have the same reaction time. That's going to get rid of a possible variable. We're also assuming that we're working on a nice road, so there's no bend or incline that might affect the way the brakes stop the car. So we'll just be on a nice straight flat road. Given those conditions, the reaction distance, so this is the distance that you travel during the period in which you're reacting to the emergency, is proportional to the speed that you're traveling. So I'll call it d sub r, reaction distance, equals k1 times s. S is the speed and k1 is a constant of proportionality. Then the distance that your car travels while you're braking is proportional to the speed squared. So the distance while braking is some constant of proportionality times s squared. So during an emergency braking situation, the total distance that you're going to travel is the sum of those two. So it's k1s plus k2s squared. That's a quadratic polynomial with no constant term. So that's the model that we want to generate the coefficients K1 and K2 for. Okay, suppose safety engineers have collected the following data. At 15 miles per hour, the stopping distance is about 55 feet. At 25 miles per hour, it's about 105 feet. At 35, it's 160. And at 60, it's 350. We're going to fit a quadratic with no constant to this data, and then we'll use it to predict the stopping distance when going 80 miles per hour. Now you might wonder here, do I need to worry about miles and feet? And you don't. You could just ignore the constants mathematically and think of this as the points 15, 55, 25, 105, 35, 160, 60, 350. You're just trying to fit a curve through these numbers. So then when we plug 80 into our model, what it's going to return us is some number larger than 350, and that's going to be a measurement in feet. Okay, let's identify all of the components here. The speed is the independent variable. So x is going to be 15, 25, 35, and 60. The vector y of dependent measurements is 55, 105, 160, and 350. What we call m that we're looking for is really just the numbers k1 and k2, those constants of proportionality. Then the matrix we're going to use A needs to return us a model that will have no constant, but will have a degree 1 and degree 2 term. So S is really like X. I actually could be calling this S. That's the speed we're going. Those measurements are going to form the first column of A, and then the second column of A is going to be their square. So A is going to be a 4x2 matrix that's going to look like 15, 25, 35, and 60. And then in the second column, 15 squared, 25 squared, 35 squared, and 60 squared. Okay, let's finish this problem in MATLAB. Okay, let me do the vector x. I could call it s again, but I'll just stick with x. This is going to be 15, 25, 35, and 60. I don't need to also do a vector that's those entries squared. I'll show you how to do this in MATLAB. Y are stopping distances. These are 55, 105, 160, and 350. That's all we need. And then A is going to be x squared with the array operation here. You can run that and see what it looks like. You can see it's a 4x2 matrix. The first column is the speed, and the second column is the speed squared. Okay, our vector m containing those constants of proportionality we're going to get by doing the inverse of A transpose times A transpose times y. Okay, so there's m. So K1 is 2.93 about, and K2 is 0.05, let's say. Okay, I'm going to suppress that output. Now we'll make a function. This is going to be an anonymous function of x. It's going to be the first entry in m times x plus the second entry in m times x squared, like that. You can actually say, what is f of x, to see what it's going to do with these speeds, compare them to the y values. So about 55, about 105, about 160, and about 350. So you can see we're doing pretty well. So this should return approximately y. And now to finish the problem, we were asked what the stopping distance would be if we were going 80 miles an hour. It would be about 545 feet. So what this means is if you're going down I-40 and you're going about 80 miles an hour and there's a crash up in front of you, if it takes you a couple seconds to brake, I think when I set up this model, I crunched the numbers with a reaction time of about 2 seconds, which isn't bad. It could be slower, especially if someone's looking down at their phone, something like that. You should expect to travel quite a ways while you're doing an emergency brake. So at 80 miles an hour, you really can't stop on a dime. Okay, I hope you enjoyed looking at these problems with me. Thank you for your attention.